Hi everyone. Thank you for being here. I'm going to briefly present about HHAT's data structure using quantum and the logic behind it. So please click. On the left side, it's basically how we define quantum types. It's basically like C or Rust or any strong typed language. And in the middle, basically, it's how you define a value to a variable. So you need to define the variable, and everything with a @ symbol is a quantum stuff. So it can be variable types or functions. So basically, I'm defining the literal false to a variable of the type quantum boolean. And also applying functions, it's like similar to other ways. Just name it and use the arguments. And on the right side is basically where the magic happens. So basically, quantum types are lazily evaluated. So they are just accumulating things inside of it, classical or quantum. And when you actually cast quantum to a classical type is when actually the magic happens. So it will transpile to a any kind of Quasmin-like language, and then be executed and simulated or on a device. And then the measurements is retrieved and then analyzed and converted to the actual type that you wanted to convert. And in this case, it just returns the true. I don't know if you can see, but yeah, that's basically it. This is very overview of the language. And if you want to know more, I'll be in the room upstairs. And yeah, thank you for it.
Thank you. Next one is Armin.
Yep. Hello. Yeah, passt. Yeah, hello everyone. My name is Armin. I'm from the company ADDITIVE GmbH, and I am here a little bit exotic, I guess, because I am the product manager for Mathematica, and Mathematica has no Q in its name, so that's a difference at all. Nine. Imagine having a single unified platform where you can explore quantum algorithms, simulate your quantum systems and analyze data, publish your results without any switching the environment, and that's why that's what Mathematica offers, right? So developed by Wolfram Research, Mathematica is far more than a symbolic computation engine. It's a complete technical development ecosystem, right? And its strength lies in seamless integration, combining symbolic mathematics. By the way, we can click.
You have to let me on.
And yes, symbolic mathematics, numerical computation, visualization, and automated code generation if you want. So and I'm convinced for quantum computing, this integration becomes a real advantage. So with Mathematica, researchers can prototype and test quantum circuits using the quantum framework, Wolfram quantum framework, of course, since 2022. And model quantum states and operate symbolically, and even connect to real quantum backends, maybe classic Q-control and so on, through cloud interfaces. So the language, high-level abstraction made it possible to express the complex quantum operations in a concise and readable way, so in readable form, so ideal for teaching, research, rapid prototyping. So yeah, in its latest versions, you have the possibility for a bunch of functions for manipulating symbolic matrices, symbolic tensors, and so on. And of course, they obey the underlying linear algebra laws, of course, right? And yeah, click maybe.
The last slide here.
Sorry, yeah, it's my last slide.
Okay.
So moreover, Mathematica's notebook interface supports fully reproducible workflows. So equations, visualizations, code, and the commentary exist in one dynamic environment and one dynamic document, making collaboration, publication effortless. So, and yeah, in short, Mathematica brings bridges theory and implementation and empowers physicists computer scientists, chemists like me, and educators to go from abstract quantum concept to concrete results. So if you're interested in, there right over is my poster session there, and you're welcome. Thanks.
Thanks, Armin. So Benedikt is next. Just a click easier.
I go here. Yes, yesterday we had the use case that your mother gives you a quantum circuit and you had to verify it. Today we are concerned with the question, what circuit does your mother even give you? And this is what we want to do with the QuaST decision tree. We want to enable quantum applications, and this means enabling people that don't want to learn quantum to use quantum. And what we mean by applications is here optimization, since we also heard yesterday that 80% of industry interest is in optimization applications. And the problem here is that you have to decide a lot of things that are not all quantum, and this is what we do with the QuaST decision tree. This is what where this helps you. Click. Perfect. Now, what are the three sort of design principles that I want to highlight here? First, we have a very modular tool. You can basically do any sort of pre-processing, any sort of post-processing. You can implement your own sort of decision tree instance. We actually have done this. For example, we have integrated this with the Munich Quantum Software stack, or we can use it now. Then this is like not very sophisticated right now, but what you can really do is run this in a fully automated way. So you define your problem instance in a human-readable and machine-readable way in a JSON format. You throw it in there, and then you get a result file out that runs a quantum circuit on a simulator on a real hardware backend. How we imagine this to be used, you can already try out our low-code entry point with this QR code. Then you can use this for testing and prototyping, because also you researchers don't want to sort of care about the whole solution pipeline, but only your expertise. And then, as I already said, you can connect this to software stacks. You can use this to generate configuration files for compilers, whatever you want. And if you're interested in more details, you'll find me there in the back corner. Thanks, see you later.
Thanks, Benedikt. Next one is Guido.
Yes.
Here we go.
Perfect. So hi everyone, I'm Guido Masella. I'm CTO and co-founder of QPerfect, a quantum software company in Strasbourg, France. At QPerfect, we build the software stack for running fault-tolerant application on neutral atom quantum computers. But today I'm actually here to present you shortly the first layer of this software stack, which is about emulation, building circuits and emulating them. It's MIMIQ. It's a product of our company. It's a framework for emulation of quantum circuits, and is what we use at QPerfect for pushing the boundaries of quantum algorithm emulation with tensor networks. Click. So we had this morning an introduction why quantum emulators are important. Here we are all building amazing software, and we all know what are the bottlenecks. And we need debugging, reliable testing, and robust verification. And we cannot wait for fault-tolerant computers to provide that for our fault-tolerant applications. But in the meantime, we need emulators and software that can do that at a meaningful scale. So that's what we build MIMIQ for. MIMIQ is a universal quantum circuit simulator at the moment. It has two different engines, a very high optimized CPU, state vector engine, and a CPU-based matrix-produced state engines that can provide actually the scale that people need. It has all the features that you would want. It's universal, long all-to-all connectivity, and you can simulate any quantum circuits with mid-circuit measurements and so on in MIMIQ. And how fast it is? We have a comprehensive benchmark of different simulators, MIMIQ also is part of it. For example, here you can see the runtime and the number of qubits simulated with accuracy more than 99%. And you can see that higher is better. MIMIQ is there is the highest one. You can read more on the archive paper. But more importantly than everything, we are collaborating with different partners, QERA in premise, that we are simulating with them large fault-tolerant circuits. 289 qubits, magic state distillation, so fully universal, fidelity 1 in just a few minutes. And that is impressive. It's not impressive by itself. We are also, with BTQ, designing and testing algorithms for providing secure communications that are enabled from tolerant quantum computer. MIMIQ is available already online. The circuit libraries are open source, available to download from PIP or from our GitHub, and the local executors are also available to download freely, state vector mainly. The MPS is only available on license, on request. Please contact me or reach out to Hugo from QPerfect that is there in the audience.
And on
yes,
the poster,
thank you.
please. Thanks. Next one is Adrien.
Hi everyone, my name is Adrien from Riverlane, and so I'm here to present you a new tool, Deltakit. First, a quick show of hand. Who here is interested by quantum error correction? Okay, probably half the room. So who here thinks that quantum error correction will be eventually needed for quantum computing to show its promises? Okay, approximately the same set of people. So a lot of people. Click. Turns out Riverlane did a survey recently on quantum error correction, and 65% of the people answered that quantum error correction is, in their opinion, essential to quantum computing in the future. Click. Turns out that 41% of them said that insufficient training and knowledge about quantum error correction was one of the main pain points they had to start working on quantum error correction. Click. And so that is why at Riverlane, we released Deltakit, a toolkit composed of first a textbook, which turns you from 0 to hero. I like that expression. You start from the basics, classical error correction, classical things, and then you slowly complexify up to the surface code, where you reach a point where you can start reading papers and you can start exploring yourself quantum error correction. Then you have a library, open source library. You can just pip install Deltakit and that should work. If not, send me a message. And that open source library is here to get a full QEC pipeline from circuit generation to circuit manipulation, noise modeling, simulation, decoding, etc. Speaking about decoding, Riverlane is known for its decoders. You have access to a lot of decoders within Deltakit, and you can try them out. I just want to highlight one thing here. You have leakage-aware simulation, which is important for superconducting devices, or when you want to simulate noise for superconducting devices, and leakage-aware decoders that can use leakage information to improve the decoding performance. Click. So if you are interested, come and join us, open issues, open PRs, talk to us. Thanks.
Wonderful, thank you. Next one is Mikola. Yeah, well, almost. Mikola will be missing, so it's Yuri. Hi everyone, I'm Yuri, and today I'm with my colleague Vlad. He is there. We are from Heiko, and in Heiko we are so much distributed team that having 2 colleagues in one place is already a miracle. Some of them I see once per year. And Heiko, we are dedicated to enabling useful quantum computation as soon as possible by providing performance tools and software. And today I want to highlight our middleware stack. We provide an edge across different applications, including computational fluid dynamics, quantum chemistry simulation, financial modeling, and QML. And combining our middleware tools with our infrastructure, we are able to run our mitigation with 50 times less quantum resources compared to usual, or run circuits with order of magnitude more operations. And this all benefits across different quantum modalities. Could you move to the next one? Thanks. And what does it mean for you? Here are just some few highlights of our performance gains. On application level, you could run larger scale quantum data loading jobs, and we are able to handle up to 7 million features on already existing QPU. And we show how with this technology you could run already practical QML applications. Or you could use our circuit optimization, which is performant and fast, and runs out of the box at more than 100 qubits for different applications. As an example, you could see performance of LR QAA at 100 qubits and different depths. And you could see with Haiku, you could run much more complex and performant jobs. And last but not least, you could run our error mitigation, which is lightweight and fast. And for example, you could run IBM utility experiment with 127 qubits just on 3 credits that you got. So if you're interested and want to try it out, we're already live. So you could use a scanner QR code and sign up for demo, or me and Vlad will be near the poster and you could ask more detailed questions. Thank you.
Thank you. And now I've got a problem. Of course, there must be some sort of problem because I don't have your slide set, and I'm not sure whether it's probably our fault. We figured it out, and in the worst case, we're giving you a first slot after the lunch. I don't have your slides here at the moment. I'm really, really sorry. But we're definitely going to cover that. We figured it out in the break, okay? Then let's move on. I'm really sorry, but we definitely get you covered. No worries. And then we continue with Ran, right?
No, I'm Ran.
Oh, you're Ran.
Yeah, so there's one guy missing in front of me. So.
That explains a lot.
Yeah.
Then my deduction was wrong. Then we are here absolutely correct and as planned and originally from the beginning. So this is your slide set. You take it away.
Exactly.
Go ahead.
Okay. So my name's Ran, and I'm co-founder of Local Quantum. And Local Quantum, what does it mean? It's a low-code quantum platform. And what we provide a low-code quantum algorithm designer online so that people can design without coding and everything. They just like try it out and how to apply their quantum algorithm on their own computational tasks. And this is our vision, because when we talk to industry people, even pip install can be super overwhelming for them. I believe this is not the case here, but actually that's why we have to provide there's such a entry point that say, okay, we have graphical user interface. Please go to the next point. Yeah. And this is the front end of our solution. So from here, maybe can I just quickly go through? Yeah, people can use their application scenarios, for example, finance, chemistry, and this is mostly industry usage. If they don't know what to use, they can ask our AI chatbot, and we help them to choose the proper algorithm. And we also have some self-developed algorithm, for example, the GPT-QAOA and all these algorithms available. And then we also have the AI agent to optimize the selected algorithm. And in the future, we're going to have some simulator and also digital twins to help people validate their algorithm design via our platform. Once it's validated, they can visit different backend and run it on the real quantum circuit. And quickly, I will show you a demo that is a real use cases that we developed for Vanguard. Is also like a venture in US. And this is aiming at a portfolio optimization. And I will quickly show you how does it work if I want to start a video. Okay, yeah, people can quickly import their bound bucket and then set their so-called objective function and basically translate to the real world understanding words, and that is minimize the tracking error. And then once it's running and you see this is not really a mock, but rather like a real training on the background, and finally you get the portfolio suggestion as sketched here. So we are the founding team based in Aachen and Jülich. We have expert from the quantum theory and also quantum experiment from superconducting and the spin qubit. And we also have AI expert working on generative AI and explainable AI. Follow us at LinkedIn, and we also have website online, so try it out, and looking forward to your feedback.
Thank you. I know everything. Then we've got Sven.
All right.
Oops.
Right, so hi. My name is Sven. I'm from the German Aerospace Center, and I'm here to pitch QuasT, which stands for Quantum Evolving Ansatz Variational Solver. Click. Right, imagine the following situation. You're coming from the application side, and you bring your own optimization problem that you need to optimize for some reason. Then you have heard a little bit about various variational quantum algorithms that can actually, well, supposedly, find the minimum of your problem. Then one of the issues with, for example, VQE that you have, or that you encounter, is that you need to find a suitable ansatz for your problem. There are different choices, and you have no idea what to do. Turns out there's actually a class of algorithms that basically helps you with this. These we typically call evolving ansatz, quantum variational algorithms. For example, there's evolutionary VQE, EVQE, there's QNeat or multi-objective genetic VQE. The point of these algorithms is that they basically wrap the VQE part or the optimization part by some kind of other algorithm that chooses the ansatz for you. And QuasT implements a generic interface for these kinds of algorithms. So in particular, we implemented EVQE, where you use an evolutionary algorithm to pick a good ansatz choice and use this, for example, for the job shop scheduling problem. The library is very generic. You can also do this for other algorithms. It offers you a highly parallelizable way of doing optimization. And the resulting circuits, the resulting ansatzes, are actually pretty small. So it's very robust against noise. Now, the library is actually available on pip. It's on GitHub. You can download it easily. It's very well integrated with QuaST, so you can just run all the algorithms against the QuaST backend, for example. And I'm very happy to tell you more details at the poster over there. So thank you very much.
Thank you. So then next is President of Guppy, right?
Yeah.
Because it says Tatiana here. You don't look like Tatiana. But
Tatiana, but I'm Austin Bornia with Tatiana and with a lot more people who are working on a new Pythonic programming language for hybrid quantum and classical programs. This is mostly oriented towards like the new kind of computers, the one we are releasing at Quantinuum this year, where you are not just doing flat circuits and waiting for a result, but you're in constant communication between the classical runtime and the quantum part, and you may do arbitrary classical control flow there. So click. So what we want with Guppy is to bring the familiar Python syntax. We want people to be able to write something more higher level, like go and write something that looks like a Python syntax, a Python program, where you have like operations on qubits. You will mix that with measurements and maybe some control flow. Here you have some loop, repeatante success, all written in, again, something familiar. But as soon as you decorate that with @Guppy, we take the AST from there, we compile it to our internal representation, and then you can run exactly that in the quantum machine. Click. So we want people to stop writing the low-level flat quantum circuits. We want them to start doing more like modern modern programs. Like maybe you want to define your own classes and methods on those. You can add like call functions over there. You may have Python generics or something like that. We want to give tools for people to express their algorithms in like a nice syntax. Click. And also, it's not the same if you run your Python program, it errors out, and then you rerun it, fix something. Here, we want to be able, like if you run it in a quantum machine, an error there will cause a lot of cost in money, and also your experiment, you'll have to wait again, and so on. So with Guppy, we want to give you all the errors we can, like do some static analysis, we have linear types, and we give you some really nice errors where they tell you exactly where the thing has failed and what you may be able to do to fix it. And click. Also, yeah, you may run this in a quantum computer, but you may want to debug this, to test it, or something like that, to estimate resources. So we also develop an emulator that supports all this new architecture of structured programming and so on, and it's all public. Click, and this is last slide. It's all online, it's all open source. We have a nice web page with docs and everything, so go and try it. Thank you.
Thank you. So the next one is Biscuit. Kosten, what do you want to do it? Here we go. You can have mine.
No,
okay,
thank you. Hey, I'm Costin Janko. I am at Lawrence Berkeley National Laboratory. We are building this circuit compilation infrastructure based on synthesis. It's called Biscuit. We have a lot of happy users, and we recently added 2 capabilities that I don't think you can get them anywhere else. And they're probably going to become mainstream in compilers from now on. Next. So the first one is we are able to generate dynamic circuits from any unitary. So we figured out how to combine or how to transform from unitary evolution to non-unitary evolution, relate errors, and then we can use this technique for resource optimization. So we already have some very good results, and I think there's a lot more to explore with this type of technique. The other technique is called, we are able to generate approximations. The problem is this: when you do fault-tolerant code generation, every single circuit is an approximation of your process because of the T-gate synthesis. Now, so what we figured out a way in which we can programmatically and soundly generate an ensemble of circuits. You pick error epsilon, and the average of that ensemble of circuits reduces your error quadratically. So this is a type of error mitigation technique, if you want. Now, this combination is powerful. We can use it for figuring out new error codes. I talked to somebody that was doing repeat until success techniques. Well, both of them apply, and I think can help you do that. And we have a lot of other ideas how to use this type of technology. Thank you.
Check it out.
Now,
Thanks a lot.
One more. If you are interested, the poster is there, and I have one more slide. I'm looking to recruit grad students, postdocs, or staff. Okay, come talk to us if you are interested. Thank you.
Thank you. Niklas, now it's your time. Here we go.
Hi, I'm Niklas Glaser from the Walter Meissner Institute, and so we are a bit more close to the hardware and really looked at the optimization of quantum gates. And so, for example, you want to optimize a pulse which goes into your quantum circuits, and what you really need is a robust calibration of this pulse. And for example, you want to minimize leakage and phase errors, which may get into like complex optimization landscapes. And basically what we looked at and figured out is a robust calibration routine which can optimize these highly correlated problems and also mitigate the hardware mismatches, achieving then high fidelity gates. And so basically what we have been using is as a basis a CMAS optimization, so a cloud optimization, combined with the orbit protocol for randomized benchmarking, but then also including an adaptive cost function which adapts the number of Clifford gates and therefore the sensitivity. And furthermore, a lot of influence goes then into optimizing it to execute it fast on the code. And yeah, so if you want to learn more, I'm back there on the poster and hand over to the next one.
Thank you, Niklas. Then next one is Albert.
Yes, hello, my name is Albert. I'm leading the software activities at Alpine Quantum Technologies, and I will present briefly about the calibration of trapped ion quantum computing systems at our company. Just briefly, in a nutshell, AQT, we are a hardware vendor. We basically manufacture components, ion traps, but also whole quantum computing systems. The picture is shown here. We have laser systems in these two racks. We have, including the institute at the university, several decades of operational experience and calibration. Our systems are installed on premises at LRC and also at the Poznan Supercomputing Center. We also have systems available via the AQT cloud service called Arnica. And the motivation for my poster is some misconception about the calibration of our systems that we noticed while working with our customers, Click. Namely, that we run our systems in what we call the continuous calibration mode. We do that to have a high performance of the system, but also to have an increased uptime. And here you see a schematic picture on the left-hand side. What is the difference in the calibration mode? So maybe some systems use scheduled calibrations, where you have basically the system occupied for some hour to do calibration. And then the performance might degrade over time after the calibration until the next one happens, and then it's good again. But in our case, we do continuous interleaved calibration tasks, such that we stay at a high level of performance. The calibration tasks are triggered by environmental conditions, but also by time, of course. And here you see on the right-hand side a picture of the distribution of calibration tasks and what the durations is. This is a histogram in linear scale and log scale, just to show you more details. And you see the largest part of the calibrations are short. And keep in mind, these timings there, they include everything from pre- and post-processing, execution, but also curve fitting and analysis. So if you have questions, have a bright idea maybe how to optimize the calibrations on our systems, or looking for a job, then come and visit me at my poster. Thanks.
Thanks. Again, we've got Manuel.
Hello. So, hello everybody. My name is Manuel, and I'm happy to today present you our unified platform for quantum simulations of molecular systems, namely FQSIM. Here on the left side, you can see the general structure. In the upper two rows, we have the high-level interface consisting of several VQE variants and operator pools and fixed Ansätze, which we already implemented and which allow the user to easily execute their quantum simulations. Below this, we have the low-level interface consisting of several classes which allow the user to intuitively develop their own extensions to the already existing methods. And further, in order to execute a quantum simulation, we need an Hamiltonian. So FQSIM accepts either a PySTF object or an FCI-DUM file, which can be generated by example, for example, MolPro. Finally, we have three backends implemented. We have Qiskit and PennyLane for seamless hardware access. And we also have QLEX implemented for super fast CPU simulations. So depending on the task, QLEX can be about an order of magnitude faster than the other backends. Yes, so click. Thank you. What can we do with FQSIM? One example. We developed FQSIM within the H2Giga project, and there we used it to generate potential energy surfaces of electrode materials dissolved in water. And we did this by reducing first the problem to a subproblem and then passed it to the PySTF, and which then generated the appropriate Hamiltonian, and which then it passed to FQSIM, which takes care of the rest of over the mapping wave function to the energy estimation. And finally, here we have our plan. So currently, we have NISQ algorithms implemented, namely various VQE variants. We also have an early fault-tolerant algorithm, namely QCells, implemented. And until the end of the year, we plan to release FQSIM, and we also plan to integrate it within a flagship bundle, which will then connect it to various other useful tools. Finally, we plan then from next year on to shift towards fault-tolerant algorithms. With this being said, my time's over, so thanks for your attention and feel free to meet us at our poster.
Thank you. Don't forget to scan the QR code. So, Matti?
I think one is missing.
Yes, exactly. Then we continue with you, Nico, right?
Yes.
No problem.
Yep. So, hi everyone. My name is Nico. I'm the senior scientist of the Quantum Compilation Group at Fraunhofer IIS. And so in the next 2.5 minutes, I'm trying to convey to you a very high-level overview of what we're working on, but I would be very happy to discuss all the technical details later on. So if I had to summarize it in a single sentence, Then we are working on software solutions for the quantum computing middleware stack, and more often than not, we use techniques from artificial intelligence for that. Click. So I brought a very simplified view of how we basically interpret the quantum computing stack. Of course, at the bottom we have our actual hardware. At the top we have the applications and the interface. Below that we have quantum algorithms and algorithmic primitives. So we're also working on that. But today I really want to focus on these 3 middleware layers, starting up with the first one, which is compilation. And so for us, what we are usually or currently working on is mainly unitary synthesis. So assume that you're given your quantum observation as a unitary matrix, either with some structure or also completely random. And then the task is to come up with a quantum circuit that implements this unitary up to a very high precision. Of course, you also want to satisfy additional constraints. So your circuit should be as shallow as possible. And so what we're really developing there is a reinforcement learning agent that does unitary synthesis with simultaneous T-gate minimization. And as we all know, of course, T-gate minimization is very important for fault-tolerant quantum computing. And then next up, we got circuit cutting, which is one subfield of distributed quantum computing, where we assume that we either don't have or don't require quantum links between our different subcircuits. Instead, we do everything in classical post-processing. This, unfortunately, introduces an exponential sampling overhead. So we're also working on AI techniques to reduce that by, for example, optimal cut selection. But more importantly, there we are working towards an out-of-the-box solution for circuit cutting. So you just provide your circuit and everything else from the optimal cut selection to post-processing and all the resource estimation in between is handled automatically. And then last but not least, we're also working on quantum error correction. So there we use techniques from classical and also quantum machine learning to come up with more efficient quantum error correction techniques by tailoring the schemes either to some structure in your noise on the actual hardware or tailoring it to structure within your algorithmic primitives. So yeah, of course, this is only a very high-level overview, but you also have our poster later. So yeah, I will be there. Also, Mani, our senior engineer, will be there. So if you're interested in any of the topics and also machine learning for quantum compilation in general, I would be very happy to discuss further details. Thank you.
Thank you. So then next is Leonardo, wait. Yes. Here you go.
Hello, everyone. My name is Leonardo from Entropica Labs, a Singaporean startup. And today I will be talking about the QEC lab, loop design. Next slide. So there's going to be a small video playing. On the right-hand side, you see Entwine. You're constructing lattice surgery operations visually, and what you're doing right there is a belt state preparation. On the right, you obtain Python code. This Python code, you can take it, put it to a Jupyter notebook, and execute it. So what can you really do with all of this? You can generate circuits that you can execute. We target many languages, Steam, because everybody uses Steam, CUDA-Q, MIMIQ, you heard a presentation earlier, the Xanadu framework, PennyLane/Catalyst. We support all lattice surgery operations when it comes to the surface code. T-gates will be coming out towards the end of the year. So far, anything Clifford you can use. You can also bring your own code. You're not limited to what we have put in the open source library. You can construct things, starting from basically all the scaffolding that Ines talked about during the first presentation today. And I will add a couple, and decoders. So you can also work with active decoding. So you can try to plug in your own logic for the decoding step of quantum error correction. User stories. Some of our clients were successful in implementing QLDPC codes on their own. They were able to add BB codes, color codes, so you can customize however you wish. We had quite some success in reproducing many T-gate machinery with the graphical interface, just putting things up. And finally, a very important topic, which is quite dear to me. You can, and I really encourage using this tool for educational purposes. I think it's one of the simplest way to get started with lattice surgery, surface codes, and as we've seen, a lot of this will be super, super important in the next years. To conclude, the poster is over there. I can safely say we have some of the nicer stickers that I've seen around.
If you would have mentioned it, I would have mentioned the stickers.
Sorry, I stole an easy one from you. And finally, there is a QR code. You can get started with Entwine today. I have a small bet with my CEO about the number of people that they will sign up today. So please help me not to have to pay a beer. Thank you.
Thank you. So then we have colleagues from Augsburg. No?
Yes.
Still got white slides, right? You take it away.
Hi, everyone. Can you hear me? Okay. I'm Davide Vincoletto from University of Augsburg, and I'm here to show a couple of software that we are developing at our chair. And these are called Freedance and Sunrise. They are part of the Tequila ecosystem, Tequila being previous software that we have developed and show also at this forum for general purpose quantum computing. Click, please. And then this is an example in which we are computing a ground state for a molecule, and you can see how they behave, the two packages behave complementary to one another. On the one side, we have Sunrise, which is general purpose quantum chemistry simulation package. In this case, it holds no qubit information. It operates on fermionic level, and this leverages the abstract objects and simulate them efficiently. You can do multiple things like fermionic circuit preparation, state preparation, and emulations and measurements. And on the other side, we have Freidance, which computes optimal basis set for example, these fermionic systems. And taking a continuous system or a potential, this computes discretized second quantized Hamiltonian through continuous optimization. And together, as I said, this is, for example, a ground state calculation. You can find them both publicly and on GitHub. And finally, my poster is over there, and the whole crew is here to present it. And if you have more questions, you can find us there. Thank you.
Awesome, thanks you. So then, Takafumi. Here we go.
Oh, actually, I'm not Takafumi-san because he had big trouble on his trip, so I'll take over.
Sure.
Okay. So, hi, nice to meet you, everyone. I'm Kosuke from the University of Osaka in Japan. Today, I'll introduce Octopus. You can think of it as an operating system for the cloud-based quantum computing platform. Okay, please click. So suppose you decided to build your own quantum platform, like the IBM or Amazon Bracket. Creating the quantum chip is not sufficient because you also need a bunch of classical software components, making the quantum resource available to users. So, but as a quantum researcher or engineers, you do not want to spend much time to building and managing such a surrounding infrastructure. And that's exactly where the Octopus comes in. So it's an open source quantum system toolchain, a collection of system software for making the mere quantum chip to the whole working IT system. So being open source is at the heart of our philosophy. We believe the openness accelerates the innovation in the quantum ecosystem. So all Octopus software is released under the Apache 2 license, and it means you can freely inspect the code and customize the functionality to meet your specific needs, and even contributing your improvements back to the community. So we strongly welcome your pull requests. Not only the system software stack, but Octopus also includes the operational tool. For instance, QDash is an application for automated calibration and monitoring of the quantum device. So thanks to Octopus, QDash, you can scale your operational task with respect to the growth of the number of qubits. We actually use the Q-Octopus system to building our own quantum platform at our university and delivering the quantum resource to the users. So after all, Octopus is a very powerful and practical solution for anyone who want to make their device to the whole IT system and dive into the world of quantum research and business. So thank you for your attention.
Thank you. And then we got Philip. Take it away.
Single slide for my...
Yeah, it's on.
Yeah, no, it's on. Hi, I'm Philip. I'm the second continuum presentation today. I want to introduce to you a second tool. It's called Tierkreis. Very easy to remember name if you're German speaking. If not, please pronounce it Tierkreis, not Tirekreis or anything else. As you heard in the session yesterday, a lot of you responded, I don't use any tools for HPC when developing my quantum workflows. I was very surprised to hear this, but then I thought maybe you don't know any tools. You no longer can use this excuse because now you can use, Tierkreis, which is an HPC workflow tool. And if you don't know what it means, just look at the graph on the right. So a workflow is basically a program interpreted as a graph. In Tierkreis, graphs are first-class citizens, so you can do operations on graphs, and graphs represent your whole operations. And you can do additional cool features, like you can map over parameters. So if you want to do a parallel sweep over parameter space, you just map over this and then apply a function to this, or a graph. This lets you easily compose any complex workflow. This example is taken from a QSDI example we ran. But what's even cooler, and this is where we then start to addressing the HPC people, we can do this in a language agnostic manner. So if you run a quantum chemistry application and have some ancient C++ or even Fortran tool, technically we can use that. If you provide a very thin wrapper that handles the in and outputs, our orchestration tool can use this. In addition to that, we also have HPC native features. So if you run a cluster, for example, with Slurm, PBS, or other submission systems, users can just simply write a short description of a job they want to run. We handle everything else. We create a job script for you. We handle submission. And then once the results are available, we take them back into the workflow. And this will be also all visible in the graph. And beyond that, you can also continuously monitor the execution of your graph. So this is a static example. So if this were running in the background, you could see slowly each of these nodes turning green, telling you that your program is running successful. If you want to know more about this or other cool features that we have, please come to talk to me at the poster. Thank you.
Thanks, Philip. And last, but certainly not least, we've got Tobias.
Yes. Hello, everyone. My name is Tobias Rohe from the LMU Munich, and I'm happy to share with you Cocoon, the quantum computer user network. Our mission, our goal is to reduce the entry barriers for small and medium-sized companies. As you all know, funding for small and medium-sized companies for quantum difficulties are also targeting larger companies. Together with BASF, SAP, and Aquarius, we have built this platform, developed the platform with 5 different pillars. Yes, now a little click hell is starting, I'm sorry. First pillar is quantum courseware. So for domain experts in the domain of manufacturing and so on, to get to know quantum computing, how it works, and so on. The second pillar is the use case library. As a company, you can come to us, propose a use case. We will look how a quantum solution can look, how like a classical solution can look, compare them, benchmark them, run them on quantum computers. The third one is the quantum hardware access. So directly executing it, benchmarking it. Fourth and fifth, looking for hybrid solutions. Now we are ready, sorry. And with that, you can go to our Cocoon platform, click. We are already productive. Have a look at the use cases, at the code, how it's explained, and so on. Play around. And finally, also there's an upcoming event of Cocoon, a workshop for quantum artificial intelligence and optimization. So if you have some cool research, have a look at our flyers lying right there, and maybe we are happy to see us in Spain on the conference.
Wonderful. Thank you very much.